Hello students, in this video we'll show the equivalence of two definitions of E we learned in Calc 2. Let's recall the Taylor series way of approaching E is that E is the sum, n goes from 0 to infinity of 1 over n factorial. And so what we're going to do is we're going to actually show that this infinite series converges, right? And so let's define, to do this, we say define a n just to be the nth partial sum of this thing, right? The sum k goes from 0 up to n of 1 over k factorial, which is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, all up to 1 over n factorial. And now, of course, the standard trick, and we know that this sequence an is clearly going to be increasing because these are non-negative terms, so I have a sum of non-negative terms. If I add one more term to the sum, it gets larger, right? So we trivially have that an is strictly less than an plus 1. That's trivial. And also, I know that I can replace this 1 over 3 factorial with a 1 over 2 and a 1 over 2, right? So I can also say that this is less than what? And then also note that notice that an, which is 1 plus 1 plus 1 over n factorial, is less than 1 plus 1 plus, then the 1 over 2 is a 1/2. Then I'm going to replace this 1 over 3 with a 1 over 2 and a 1 over 2, so that's going to be a 1 over 4, right? And then I have an n factorial over there, so I'm going to have a plus all the way down to 1 over 2 to the n minus 1, like that. Okay, great. And now, of course, these terms over here sum up to something that's less than 1 because it's the terms in a geometric progression, right? So that's going to be less than 1, so maybe this is going to be all less than 3. Okay, so in other words, I have a monotone sequence that's bounded by 3, so by the monotone convergence theorem, the an converge to some number, and then I'm going to call that number E, and that number E happens to be less than 3. Okay, excellent. So the an's converge to a number called E, right? And of course we know E is like 2.718281845904523, etc., right? Okay, good. And so now we also have, from our pre-calculus days, another definition of E, right? And so from pre-calculus days, when we talk about compound interest, we had people say that E was really what? It was the limit, as n goes to infinity, of 1 plus 1 over n to the n. We were told that that was equal to E. So we're going to actually prove that the limit of this sequence actually converges, and converges to the same thing as this sequence. Okay, that's now our objective, right? And so let's define the partial sums again. Define Bn to be 1 plus 1 over n to the power of n, right? And so now I'm going to do is I'm going to use the binomial theorem, right? And so by the binomial theorem, the Bn is the sum, k goes from 0 up to n of n choose k, like that. And then I'm going to put this, the 1 over n, I'm going to give that the k, and I'll give the 1 the n minus k. And so what we really have over here is we have this. This is really just going to be the sum. K goes from 0 up to n of n choose k, which of course is n factorial over n minus k factorial k factorial, like that. And then a 1 over n to the k, 1 over n to the power k. And so let's actually examine this carefully and see what these terms look like over here. So when k is equal to 0, this is going to be a 1. So in other words, Bn is equal to 1 when k is equal to 0, right? Because that just gives me a 1 in the... In other words, when k is equal to 1, that just corresponds to the term. We put all of the n powers on 1. When n is equal, when k is equal to 1 over here, then what are we going to have? We're going to have another 1, right? And then the interesting thing comes when k is equal to 2, right? And I'm assuming that n's bigger than 2, right? So when k is equal to 2, what are we going to have over here? So what happens over here when we simplify this, it's going to be a what? I'm going to have a 1 over 2 factorial, and then what will be left over here? I'll have an n squared. So I'll have an n squared, 1 over n squared when k is equal to 2. And then I'm going to have an, on top, we'll have an n, and then an n minus 1 on top for 1, like that, okay? And so if we simplify this, what are we going to see? So one of the n's is going to cancel out over there, so this is going to be a We'll simplify this and we'll just keep going, like so on and so on. So this is a 1 plus 1 over 2 factorial. And then we'll have a what? And that's going to be times a 1. So, of course, the n over n is going to cancel out. So n over n and then n over 1. So 1 minus 1 over n, like that. So that's the next term of the sequence. Let's look at the next term we're going to get. The next term we're going to get is going to be a 1 over 3 factorial, right? 1 over 3 factorial, right? Then we'll have an n cubed, like that. 1 over n cubed. And then we'll have a what? Then we'll have on top, we're going to have an n, then an n minus 1, then an n minus 2, like that. And by the same trick, we're going to say this is a 1 over 3 factorial, and then a 1 minus 1 over n, and then I'm going to have a 1 minus 2 over n, okay? And of course, this pattern is going to persist down to the last term over here, which is going to be 1 over n factorial, and then a 1 minus 1 over n, a 1 minus 2 over n, all the way then times, down to 1 minus n minus 1 over n, right? So that's the way we're going to represent the bn's, plus all the way down to 1 over n factorial, and then what? And then a 1 minus 1 over n, times, 1 minus n minus 1 over n. Now, what can we say from this expression over here? We can say automatically that these terms over here look like what? The bn's look like 1, 1, 1, 1, and then a 1 over 2 factorial times something that is smaller than 1, plus 1 over 3 factorial times something that is smaller than 1. 1 over n factorial times something that's smaller than 1. So this proves that the bn are strictly less than the what? Are strictly less than the an, and that gives me one of the limits over here. So in other words, I know, and of course, we can also see that when I write down this representation for bn plus 1, we'll have exactly the same form, but I have a bn plus 1 that's going to be slightly larger than this because I'm making the denominator smaller. So bn plus 1, again, slightly larger than an extra term over here. So clearly, the bn are an increasing sequence. So bn, the collection bn, are increasing. And they're bounded by the an, which in turn are bounded by 3. And that implies we get one inequality for free. The limit as n goes to infinity of the bn's are less than or equal to the limit as n goes to infinity of the an's. And that, of course, is equal to e. So we've just proven the limit of the bn's is bigger than or equal to e. Now what we're going to do is we're going to fix an m. Okay, so fix m less than n. And then what can we say? We can say that bn, like this, bn is bigger than or equal to, just strictly bigger than actually, 1 plus 1 plus 1 over 2 factorial, 1 minus 1 over n. And we do this all the way down to 1 over m factorial, 1 over m factorial, and then 1 minus m minus 1 over n times all the way down to the product 1 minus 1 over n, like that, okay? In other words, I take this bn and I look at the first m terms of this bn sequence like this, and now what I'm going to do is I'm going to let n go to infinity. So as n goes to infinity, what does this say? As n goes to infinity in this inequality over here, we have that the limit as n goes to infinity of the bn, which we know exists, is bigger than or equal to what? Bigger than or equal to am. Because what's going to happen over here is that all of these terms that are, as n goes to infinity, are going to converge to 1, right? And then I'll have a 1 plus 1 plus 1 over 2 factorial plus 1 over m factorial, and that's am. And now I can let m go to infinity in this inequality, and therefore we conclude what? That the limit as n goes to infinity of bn is bigger than or equal to the limit as m goes to infinity of the am, which we know is e. So I've now proven the limit of the bn's are larger than or equal to e, and the limits of the bn are less than or equal to e. So our conclusion, therefore, is that the limits as n goes to infinity of the bn's are also equal to e. So in other words, the limit of this sequence over here of 1 plus 1 over n to the n, and the limit of this sequence over here, those partial sums in the Taylor series converge to exactly the same value. So those are two equally valid ways to represent the numerical quantity e, the base of a natural logarithm, either by its Taylor series or by this binomial limit over here, which comes from a sort of a continuous compounding of interest sort of idea that we learned about in pre-calculus. So we have proven that those notions are identical to each other. Thank you very much.